Hey, it's recording. Okay. So now we have kind of read through on how diffusion works. We have, we talked about how we built our scanner and the driver for the rotating base. So you know how to build one of those. We had a simple scanner and all of you have collected data. And everybody was able to get the shared files. Yes, awesome. All right. So now what we want to do is the last part, which is to think about the inversion. So I want all of you to help me here for a second. How did the inversion work when we did like FBP or ARCs or anything of that sort? I don't know, either one of them. Doesn't really matter to me.
Just a straight line path.
Okay. Now, if you remember for one of those situations, we had a slightly alter, right? So maybe here's my object, and whatever, we had established some grid. And we had an emitter, but we had like an emitter array. Right? And then we had a detector array. And we can imagine for each one of these, the emitter, we had an emitter detector pair that went through, and that was kind of our reconstruction. All right? Now from this drawing, so that's kind of one area. How do you know what I reconstruct things on? Right? Got my line, straight line and whatever, but what do I do with that?
Figure out which are involved with that.
Which ones are involved? And how did I do that?
X cosine, my sine,
Okay, and x times cosine what?
of the angle.
Okay, so we had a background reference angle. Let me, I guess actually blue is pretty good because that's the right side, whatever. Here's my thing that's referencing it. Here's my x-axis. And so I've got an angle. Technically what we were concerned with was this angle here, right? But we noted that that angle is this angle, which is related to this one, and that one and this one are complementary, right? Complementary angles adding up to 90 degrees. Because that's a 90, the line makes a 180. So this one has to be 90 minus theta. All right, when we're looking onto the line. Now that is a phase shift, and we remember that phase shift in essence flops the cosine and sine, and that's why x was multiplying cosine. Remember we said we kind of expect x and y to have multiplied each other in some sense, but the phase shift, right, of 90 and cosine and sine being related that way, meant that we had our x, right, minus cosine, right, and we added, x times cosine plus y times sine, not minus, and that was equal to some constant. Okay, now, that is not a good, okay, that should still keep recording. Let me, there we go, bigger picture. Okay. So anyway, we were concerned with this angle theta, that angle theta, 90 minus. All right. My blue pen is blotting. Okay. So that gave me this equation, right? This is the equation for a line. Right? And we just remember again, this just comes from y equals mx plus b, right? And then in essence, to get to here, we noted that m is the change in y over the change in x. Right? So if you multiply through by change in x, you have basically change in x times y, right, is equal to change in y times x plus b. Right? And that's why I was saying you expect a y and an x to multiply each other from the standard line equation. Oh, sorry, and I should have this was multiplied by delta x because I have to clear the delta x through. All right. Except that because of the 90 degrees shift in here, it flipped the cosine and sine, and I would expect a sign difference when I bring this one over. But again, when you flip this and then do the conversion, you end up with a minus sign on that term. So it just cancels it out and it all comes to the other side as positives. That's another way of thinking of what we did, right? We developed it a couple different ways. Whichever way you like to think about it is fine. But the point is, we basically took kind of your standard line equation, put in the geometry, and we got this, right? And the cosine had to do now, again, we're back to theta. So this is just cosine theta. S is just sine theta, right? And this constant came from this, but, you know, we can calculate that in whatever we want. But how do I know how to do this to figure out where to mark the paths? Right? And what's x and what's y? So we made a mesh grid. So what are those x and y points then? It's the centers of each of these. And it's small enough to dot all of them. So in each one of these cases, we're really calculating this distance. Right? Each of these points here has an xi, yi value. Right? And mesh grid just calculates all the xi, yi values, and then when we take those, you know, the x means all of the x1s for the whole grid, but separated in their own little bins, right? And the y means all the y's of every one of those things in their little separate bins. So when I just did x, y, I, it did a whole bunch of xi, yi's, right? Yeah.
So when we go to write our code, we just know the line, right? No, we have to.
Yeah, your big thing is you just have to figure out which one of these ones to mark.
Yeah.
The result of that statement, right? Because it's basically you're going to do the same kind of a light projection that's on there, right? The brighter the light, the less stuff is there, right? All of that is the same. The only difference is which squares do you mark. That's actually the only difference in this, right? In your case, you know, there's only one center and they all go, wee, you know, following whatever paths we're going to decide, right? Technically following light diffusion, but we can approximate it a bunch of different ways. So the question is, how for each one of those individual, from the center to a light pair, and then we have rotating angles, for each one of those ones, how do you know what the paths are? Does that make sense? Okay, so, you know, and all I'm trying to do is get you to think about what you did before, because really, this is only like 1 to 2 lines in your original code. It will be worse in this code, but it's only going to be worse because it's not a simple straight line, it's a curve. So once you figure out how you want to mark those, you realize you don't even have to just do a line. You could pick a whole little fuzzy region that it's based off of. All right, that's what I was saying. You could take that picture of above and, you know, get the top and flip it, you know, to where your exit is, and it'll have the same spread characteristics coming back in, just going negative at the time. You don't have to worry about that. You're looking at it over that. And you can see the pattern between the two just from that, right? That's sometimes called emitter-receiver characteristics, right? It's a similar type of an idea that you would do in any other type of a setup, just visual. So we just have to mark them, and we want to mark them simply. Now, one way you could do this is you could just kind of pre-calculate all the paths you want and pass the A matrix in. Right? So you could just make a separate external function that took a look at every possible angle. Right? It could just say, what is the path from the center point on one side, because the laser hopefully was pretty centered, right, to wherever your pixel is. And you can just take your camera and just kind of draw the line straight coming down to the edge of the object, right? So you could just make an external thing that calculates all those and just marks the A paths, stores them in a row, and then inside your function to do the reconstruction, you pass it the A matrix. And then you just turn what is my angle and what's my position pixel-wise along here to be able to say what's the, you know, what's the output that I want from that, which one of these A do I grab? And then you just use that A and spread it exactly how you would have either for batch projection, it's a spread, right? You know, for art, you're in essence, you calculate that thing and take a look at the difference from what you measured and readjust them according to their differences. Right? But that's what the rest of the function does. So you can literally just replace this by an external lookup or get an equation for your thing, which is nice with like the cubic splines or other ones. They're equations, they're non-linear. Right? But that's what you would have to do. And then to get the distance. Now that's the question. How did we calculate all of these distances?
Are you saying the distance from the line that's acceptable, or what the actual distance is?
The distance from the line we want to the centers.
Okay, yeah, you can just do that with the x cosine.
You stick them in the X and Y, and it's, but you'll have to get different coefficients and a different constant, which have to do with the shift. Right? So this shift right here, that was the last little bit that comes in. This encodes the theta. This constant, the B, was related to where you are along the axis. Right? In your case, it's going to be drastically different. Maybe you store the coefficients you want, like I say pre-calculate. And then you could just stick them in this equation and go. If you pre-calculate it, you've already got the A matrix, who cares? The only reason you're doing this, if it's less than a distance, you marked it a 1. Otherwise, you left it at 0. Right? If you pre-do it, you just pre-do it and check and see for each one. Right? If you pre-marked it with a 1, then go ahead. I would do that as a sparse matrix, because otherwise you're going to waste a lot of space. But I mean, that's MATLAB, so who cares? Just don't make your grid too fine, and then you can use a dense matrix, and who cares? You will have to vectorize if you're pre-calculating them, and then just store them in a row. And just make sure you store those rows in terms of position along the camera, right? And angle, because you have the same setup here. If you do the 8 fixed pictures that we took, then you've only got 8 angles, and then depending on what resolution you're going to downgrade your camera to. Remember we said your camera is way too high a resolution? That's not technically, that's not actually true. You can actually choose whatever resolution you want, but computationally you can start to see it's a pain in the butt, right? Because the number of rows you're going to have in your A matrix is going to be the number of pixels times the number of angles that you took it at. So if you're doing like 1,000 pixels across this object or something, then you're gonna have 8,000 rows, and then there'll be one column for every voxel inside of the object that you're reconstructing. So that'll just kind of get ugly fast. But hey, I mean, that's your call on that one, right? Does this make sense?
I have a question. So
Sure.
I understand that once we get the paths, we can turn that into that will be a matrix of just ones and zeros, the ones being the boxes that I went through. Once we have that, we can vectorize it, and that'll be a row of our A matrix. And I get that the A times X equals B, and we can just use whatever algorithm.
X is what you're thinking is the extinguishment coefficient,
Right.
and B is your measurements.
Right, so I was just wondering which matrix multiplication in the book corresponds to that A equals B. Because there's two two major matrix multiplications that I found. And neither of them really seem to kind of fit that, I suppose.
Yeah, I don't remember the equation right off the top of my head.
No problem.
You know, actually, let me see, I should be able. Oh, this won't make it onto the thing because I don't have it recording the book, but I can at least pull it up for the rest of us. PC. To not waste space, I wasn't recording on there. Let me. Okay. We need this. This? No, wrong one.
So the main one that I'm looking at is on page 12 in the algorithm section. Page 14 of the PDF, page 12.
Oh, 14 of the PDF. Okay, so let's see.
Or if whatever you'd like to find out. But the main one here is this A times the phi equals B. Is that what we're doing, or is that not what we're doing?
Let me see what they're calling phi again. I don't remember. I think that is their flux density,
Yes.
which is the. Yeah, so this, and are they saying that's the photon density in the, going through the pixels, or? Because how you group things up, right, there's a couple ways. You could do, what are the photons passing through a particular area, right? And that is actually proportional to what you're doing. It's not exactly what you're doing, but it is proportional to that idea. We're looking at it in terms of how many of them get removed, and normally phi is how many go through. So we're kind of doing 1 minus that.
Okay.
Right? We're saying how many got knocked out.
Okay.
right? So if you take total amount minus that, you would get what we're kind of measuring. And we usually do those that get knocked out because that's just related to the physical quantity we care about. Right, that's the extinguishment coefficient. But they didn't want to directly distinguish between scattering and extinguishment. So they just kind of lumped them all together. So they're not drawing it out exactly the same way that we are doing, but it is a similar one.
Okay, so my train of thought was, I understood the methodology that we're kind of using where you just kind of plan out a path for each photon, figure out which boxes it goes through, and use that to figure out how much atrophy it would get, or how much absorption it would get.
Yes.
I was trying to relate that to what they were doing, thinking that they were analogous.
Well, and they are fairly analogous, but it's not exactly the same on the way that we are writing the two things.
Okay, all right, that makes sense. Because I was just getting a little confused trying to equate them. I couldn't.
They're still trying to keep the light going through is the main thing they're solving for.
Okay.
We're drawing it out. That's not exactly the way most people do it in other areas.
Right.
So I'm trying to make ours look the same way you did in X-rays.
Okay, great.
I would say within this particular field, this author was one of the early ones in it. And so his notation is fairly common in this area. So it is a one you'll see frequently, but it's just not exactly the same as what you did earlier.
Okay.
So I'm just rewriting them. But the concept of what they're doing, right? I mean, the way they generated each of these, their A is a little more involved than our A because it's not just the path. It is the path location, but it also has these other, they've drawn a lot of these other coefficients out. And we're lumping the coefficients on the X term we're solving for because we're trying to solve for the X.
Right.
They're not trying to solve for those, they're trying to ignore those. So they drew those into A and just kind of swamped them and are finding ways to approximate them. All right. So realize whenever you break things into two things multiplied by each other, how you actually separate the term, how you factor it, will determine what you're looking for, right? If all of a sudden you wanted to try to solve for what was in the A matrix in ours, you'd have to factor those out.
Right.
And you take the terms you were solving for, but you know now, and you bring them in. Just multiply them through and you spread them down.
Okay.
Right? We just factored differently.
Right.
This really is only the difference, but the equations are actually the same.
Right. Okay. Right.
Yeah.
Because I understand the way that we're doing it, but I was trying to get an exact similar thing with neighbor, and I just wasn't finding it.
So what the way they're thinking about it, and it makes sense. Imagine if you were doing this from ground zero and you really, they were doing this decades ago too. So they weren't as familiar with X-rays. If you look, the people doing it had more of a background in some of the other areas, right? So it was just different, right? If you're used to X-rays, you're like, oh, let me just draw a straight line. Well, they know they're not drawing just a straight line. It's like, well, that's silly. Why would I factor in that way, right? But then what we noted is the straight line just ended up marking locations. So who cares? You know, if we want to mark, you know, if we kind of think of it pulling back to what I've got on these, if you want to think of a particular path as following a, running off the edge, kind of smeared. I've got the curse of the bad pens today. I just stole those off my desk. Okay. So I was gonna try to do everything multicolored, but I might not because Alright, if we wanna think of this in terms of just laser light comes in on this end, right? And we're reading our detectors and let's just make it simple and make them exactly correspond one to one. Right? You know, their thought is we would just mark down here and go, you know, that if I'm doing a straight line path here, maybe, you know, something like that or whatever, right? But we don't have to just do that. We could say, hey, look, it follows a path more like, you know, this.
Right.
And I can mark multiple locations to account for the spread and the coming back. Right? And I'm not just limited to an actual linear path. I can make all kinds of weird curvy paths that come through and maybe coming down to, you know, from here to here. Let me see if the red pen writes. Right? Yeah. Right? This would be an X-ray path to this spot, but maybe for us, it follows a spread out, right? So we could actually just do that. You could actually go in and manually write them if you wanted. There wasn't so many stupid different patterns that are out there. And that's why we want to do a little bit of the curve shaping when we describe what they are location-wise. That will save you a lot of trouble just because it automates their location finding. But we could technically just draw them by hand if we really felt like it, and mark them. And by allowing some spread, you'll lose some resolution by spreading them, right? Because you're spreading the areas out. But you'll also, you will gain some accuracy of how things spread around and things of that sort. So, you know, that's kind of the just looking back. And again, to their thought, this isn't readily apparent at first, unless you kind of really dug around on the x-rays, because otherwise you just think, oh, their scenario is just different from what we want. Right. And so that's why their assumption is what you're going to do is do a Monte Carlo simulation on their software with the diffusion, and you'll get all the diffusion paths. That's the pre-calculated A. So their forward problem they solve first is to get the A matrix, right? And then they've, at that point now, because they did the forward solving, implicitly, it's not just a path, it also includes how much light was lost on it. So if you solve this, instead of just thinking of it as paths and putting, you know, all the effects in the voxel locations, if you think of this as the actual voxel map, and you've done a simulation, so you know the forward position, now your simulation could be wrong, right? But that's why they talk about comparing your computed versus your actual photon density. So that's kind of what their basic assumption is. You assume it's a big old bag of water. You project what would it be if it was a big old bag of water? What would all the light paths be? What would the extinguishment coefficients be? So on and so forth. What would the outputs be? And then you take a look at, I've now got these measurements, and now I'm going to reverse them back along those paths. So if you think about that, you go, oh, that almost kind of makes some sense, because their original thing, they're like, well, how do I know what path it followed? You know, well, truth is you don't, right, unless you simulate it. X-rays, you know exactly, but in our case, we can make some pretty good guesses. Now, if we only did a straight line path approximation, we'd be off and we'd misplace some stuff. So we'll get some errors on it. In the case of a large coin cell battery like I have, some things will be completely obscured, and if you only did a straight line path, it will say that it should be completely dark, but it won't be dark. Because the reality is, there's some of these other ones to the side, and if the coin cell blocked these, for instance, I can still get a measurement here in the shadow zone because it goes around. Right? And so there is actually an advantage to including some fuzziness to this. Right? And that's something that can be kind of done on the in-between, and that's one of the things I want to talk about here in a sec. You know, how can we do some of these to get some oddball shapes without having to hand draw them? So far, so good? Do we think we understand this one here, that once we can figure out a mapping of those, the rows of an A or an equation, we can figure out which ones of these we want to mark? Do we feel comfortable with that? So then the only question comes up, how do we get those equations? Is that fair? Awesome. All right. The first easiest ones are going to be like the straight line path, the cubic spline path, things of that sort. So let's just kind of walk through how we do the straight line, and then we can take a look at each of the other ones. And then we'll talk about how we can use some of those to actually get some of the other spreads. Okay. Sorry, this is becoming more monochromatic as my pens are doing badly. Leaving blurbs on this one too. Yes, this is a rule for me to go. The really nice gel pens evidently do not work as well for me as the cheap old pens. Okay. Here we go. Laser comes in. All right. What we're going to do, let's say we want an exit over here. Straight line path we can mark. All right. This one will be fairly straightforward, right? As I rotate the angle, that's going to just kind of change our grid area. But we can easily get this one here as a line. I've got 2 points on the outer edge. All right, for my grid. So I can determine, we use those 2 points to determine the equation of the line. And then once I have that equation of the line, I can take any of these ones on the mesh grid to determine if they're inside that range. By using, I take the coefficients I used to solve from these two to then come back in and stick the x, y in. So you use the ones I mark 1. And we're going to consider the line in this form. 0 is equal to a y plus b x plus c. Right? For a line, we have 3 coefficients in this kind of generalized form. So I can figure these out. Now, there's a straight multiplier through on these. So let me explain. On the first one, you might see, oh no, 3 equations, 2 unknowns. Right? How am I ever going to solve that situation? Right? But the reality is, we know a correlation between A and B. Right? Because we know that the A over B is your slope of the line. Right? So that slope of the line is related to your angle. So we can actually just use the fact that, let's see, it's actually B over A has to be equal to M. Right? And we know the M has to do with this one's theta. Right, the theta of that line. Right. And the theta of that line is relative to this, right? So we can based on what your offset position is, right? My exit over here, this is where my pixel is. This is the camera pixel. That gives me this location with a group of camera pixels. And the laser is in the center, right? So by knowing these two positions, you know these two parts, right? Offset from center is done by pixel location, and this right here is just the distance across the object, which is going to be the same in your picture. You'd have a photo, you've got that object in the center with our motor. Here's my object that's rotating, here's the motor, and there's the spindle, and you're going to cut an image out of it, right? This diameter is that diameter, right? So by knowing your offset, you know essentially the overall length of this thing. So you can easily calculate this little triangle that fits in here, right? You need that distance from the center line. And you need this one from that point intersecting it to that other side, and that gives me this angle theta. Right? You can pre-calculate that for every stupid offset position. Right? Do we agree? And then for my line here, it's just rise over run. But that's rise and run. So you can get M directly from here. Right? So your offset position, but this is delta to this center line, right? And then you're going to have a theta angle that will be the center line angle plus what you calculate here. So let me just, maybe I'll call this phi. Maybe I shouldn't call it phi, they use phi. Theta 2, right? Delta theta, whatever you want to think of it. Right, your position is going to perturb theta because there's an angle to it. Yeah.
So, do you recommend rotating? Well, because we're taking different angles. Do you recommend moving the laser position in our model, or moving or rotating the actual phantom in our model?
I would consider it that we're going to keep the object basically fixed in our minds, right? So if you're thinking of this on here at some offset area, as far as we're concerned, we've got, laser beam coming in, right? And then we're kind of cutting this thing. So I would consider, if it was me, when you kind of draw the boxes up, I would consider any box that's outside as waste. I would only worry about the ones that actually intersect the object. But I mean, whatever makes you happy on your own recording of it. If you do include other things, then just make sure you keep a straight line path for those. But it's going to hit, come through, and then it does whatever it wants to do. That would be the normal straight path, but what it actually does is it curves down or whatever. Right? And then you've got your camera over here, and these are your camera pixels, right? And then this, we're taking it here. So where this would have hit, whatever, let's say it would have hit here, now it hits here. This offset creates, for a straight line path, you're going to take this, right? So this is some angle theta 2, right? And it's a delta to the center line laser, where this one is related to, this is theta, so this is theta. Right? So you've got this angle and you've got that angle. And that effectively gives you the combined angle to the original system. right? Because this is an original system line that the object exists within. So you know the laser rotates by that much, but when it comes in, it bends if you're doing straight. And it bends by this theta 2. That is an additional bend angle. And if it's over on this side, it bends more, right? Right? So I would have this theta plus this theta when it's on this side of it. And on this side of it, it's this theta minus that theta. This is going more back to straight. But that gives me an effective theta. This is a straight line. Now you got thetas. You know, then you just have to get your offset, which is just how far left versus right is this thing shifted. And that can be solved a number of ways. One way you could do it is you could solve for it sticking in the point. I know where the laser hits. You know, you just project the laser to where it hit on the object, stick that point in, solve for the one missing coefficient. Because you can get that in this case, if you're doing straight line, these are your cosine and your sine now because of this relation. So to find this, right, you would solve for this one by using a known point where the laser hits. That's one of the endpoints of your straight line. It's the same for all of them, so that's a natural one to pick, right? Because they all have to go through that one point. So you just take where that one point hits, that's your X and Y location, and then solve for C. Now you have that C value, you have all the equations. Then you can go, okay, now this is fixed, that is fixed by whatever you solve for by the entry point. Right? Now you know ABC. Now it's exactly what we did before. Now you do, you know, A times Y plus B times, you know, times X plus that C for the entry. You know these now. So I'll star them or something just so I remember we know them. And then the X and the Y are from the mesh grid. You calculate for every point. And this, instead of equaling 0 anymore, 0 is if it's on the line. Whatever this calculates now is the distance from the line. So then you can just say if that net distance is less than, you know, whatever the thing you want to pick, half, you know, 1/√2, 1, whatever you pick is a reasonable distance for it. You know, you could even potentially on this one pick it to be like 2, make it a really fat line, right, to account for some of the diffusion. Then you say it's in there. And that's your path, then just the rest of arc goes the exact same. You're literally just replacing instead of cosine sine and the calculation based off the projection position. You're just replacing it with this slightly more complicated way to get the angle. But otherwise it's exactly the same. Right? And it'll vary point to point because you've got your lines are bending outwards. Does that make sense for straight line path? That one will fit in. Again, it's going to be your worst image quality, right? It's going to be the worst accounting for diffusion, but it'll be really simple to build. There's something to say for that. Yeah.
Why are we talking about the height of the object? We just like take a middle.
This slice. I wouldn't pick the exact middle. So the object when I created it, let me scroll this down for a sec. So anybody look at it and recognize what that was?
What are we talking about?
The object you were imaging.
The battery?
There's a battery inside some hot glue.
Yeah.
Anybody recognize what that shape was?
You said no image.
K-cup. Yeah, it's just a K-cup. So what I did is I put this in, and the battery only covers the bottom part of it. I put glue above it It was hard to measure how deep it was. I was trying to make it about twice as deep. And the reason was when the laser shines in, if it was angled exactly the way I wanted to, and it got bumped a couple times, so you never know if it's perfect. The laser was supposed to shine about here. So on the, like if you grabbed at like the bottom quarter or so, the idea was you'd get a nice image of the shadowed object. If you went above it, it should be completely bright across it. That would be the reference. Remember they do their forward calculation and they find out what was the computed brightness, how bright should you get? Well, that should be the object, what would happen if it was just constant material. But that's what the top part gives you. So the idea was we could potentially take something from that top part, a thin slice, right? And you want a little bit of thickness to average so that if there was speckle variations or something, it would average out. It just gives you a little noise reduction. And you don't want too thick so you don't get other effects into it. But the idea was potentially you could use that top one to compare, that's how much light I should have gotten. And then when you look at the bottom, that's how much you did get. And if you wanted to, you could do differences of those to flip them like into their form. So if you did the top one minus the bottom one, you'll kind of get the exact reverse. You'll get the negative image of it. So that was the thought. It left it open to you. And I wouldn't have to make you remeasure it because I hopefully put enough glue in. I don't know. It looked like it was kind of in that ballpark range. You'll have to look and see on your pictures to see if it's useful. But that's why I actually made it thicker than the coin cell. So don't just grab the middle, because if you grab the middle, you'll get kind of a weird blend, and it won't do a good job. And the coin cell actually kind of curves on this part. So, if you grab dead in the middle, you're probably going to get a really ugly thing. So maybe get it a quarter to a third the height, something like that, probably would be pretty consistent. That's my guess anyway. Make sense? Dude, it's a good question, right? And part of what I want you to do with this is, we're treating this like we're just developing a whole brand new system. Because in a sense, we kind of are, different from what anybody else did. Right? Throughout your career, you're going to build different types of things. Right? The best thing to do often is get a good idea mathematically, the foundations, then do something. Right? As long as all of you do something, we do reasonable calculations on these, you're pretty set. We're going to write them up and document them. Maybe we discover, we should have done this and we change something later. It's no skin off my nose. As long as we're doing good things, I'm still happy with you, right? I want you to try crazy stuff and be willing to fail a little bit, but write it up well, right? That's what's going to leave you in a good spot to invent new stuff. If we had all the time in the world to develop it, we'd go on and do whatever. I think we're in a good position though. So we feel comfy with that. I know it can be a little bit scary. I want it a little bit scary, but I want you to be adventurous and know you're not going to get whacked if you're adventurous. Be adventurous. Try something cool. Right? Yeah.
So when I was putting together kind of my geometry for this, I considered doing slices, and I know that's what you recommend, but more intuitively, I kind of imagined that if we just start our light source at whatever Z height it is, then we could do the path kind of in 3D and have it go up or down in Z.
You could, right? And I was actually, my first thought was to have you do that. But then you have to also do these equations in multiple dimensions. And I'm like, in the amount of time we're going to have, a week and a half, whatever, at the end of the semester to work through it, I don't know if there was enough time to do 3D.
Okay, so just do slices.
Slices are all I need.
Okay, great.
Now, if you want to try something really cool, and you want to try 3D, this would be my recommendation. Obviously, the 1D straight line is pretty simple, right? So do that, and then add slice thickness, right? And a 3D line is not that much more complicated. You can just do this in one dimension, you do the other one in another dimension, you solve it for both, and you'll line it up. And that's about as much time complexity as you would have to do. So if you want to do the 3D one, let's say you do the straight line path, and then you could try to just figure that extra one out and away you go. I think it would be way too ugly if you were trying to do that and you were doing curved paths or other things.
Okay. Yeah, I
So
was
just for time's sake, I don't wanna,
I don't plan to do that.
you know, but I would encourage you just to think about it, even if you don't wind it up here, think about what you would do. The process of thinking about it, make yourself a couple notes, what it would look like, you know? You wanna get some extra credit counted towards it or whatever, shoot it to me, right? But think about those type of ideas, because that's the things, maybe it doesn't go into the 1.0 version of your product, but it might go into the 2.0 version of the product coming around. And having those ideas in advance, even when you're trying to think about it next time, you've kind of already laid the, you know, the structure for the whole thing, and it becomes a lot easier to do. Cool. We good with straight lines? Okay. And then there was one pen that was working well. Okay. Okay, so let's have we'll do it at angle coming in. There's our theta. There's our camera. Oops. There's our theta again. Let's get it straight. Okay, let's, for a sec, let's just do, fair enough if we just do maybe a quadratic, because I think quadratic will give you a pretty good shape-wise for these. All right. What I would suggest for a quadratic is not to try to match it perfectly here, just match position-wise. Okay. So we've got a quadratic here. Right? This is the equation for a quadratic, a x squared plus bx plus c, right? So we've got those, and then I'm just going to put the dy here, equals 0. And I have to solve for these. Fair? Okay. Now, do we agree that there is actually one redundant parameter in here, and that I can normalize this? I can take any one of these things, and I can divide by e, right? 0 divided by e, as long as e isn't 0, is still 0, right? So I can go through, and I can divide by e on every one of these. Fair? Okay. So I can, in essence, knock one of these parameters out. Without loss of generality, let me make e equals t. Is that fair? So I'm going to actually consider, and I'm just going to rewrite it as a again. So I'm going to say 0 is equal to ax squared plus bx plus c plus y. I just wanted to do that to explain why I'm just going to write plus y when I was sweating stuff before. Right? Now, that describes whatever this is. I now have 3 unknowns. I need 3 equations. So I have to give you 3 pieces of data, in essence, to solve for this. Or here you go. Here's point 1. The equation has to be consistent for this. And you have an x and a y, so I can solve that in, and that'll give me 1 equation. Right? So this is point 1. And I can find that by its depends. Here's my center line from the laser coming in. That is completely dependent basically off my position and then projected to the outer edge of the circle. Does that make sense? So this is going to be a position. What's your offset from the center of your camera. And again, your camera, we don't mean the center of your camera. You took a picture and you got the object. We mean the center of the object, that center pixel. Right? So when you look at your camera picture, right, I've cropped it so I took a road just across your object. The very center of that object, right, that's what I'm measuring my offsets from. So I can take that, I can do that same spot on the circle. What we want is then, here's another one. They're all also going to have number 2, where the laser is going to hit. Right? The laser is aimed at the dead center of the array. Right? So it is, as far as your camera is concerned, you know that center pixel area through the center of the one, it's at the far opposite side. Right? Does that make sense? So that location is going to be just completely determined by theta. All right, so to find this one, it will be theta only. To find this one, it'll matter what theta is and your position on the array. Which pixel block did you combine it into? Good? Now I've given you 2 equations, right? And again, this is an XY pair. You just put the X and the Y in, you'll get an equation, right? And it's equal to 0. It's got to be on the curve. I have to have one final thing. Can anybody else see anything you know is absolutely true for these? You do know you're starting very good, right? Yeah, you know this is exactly consistent with the laser, right? So what is that? How do I impose that condition?
Well, with power rule, you turn the coefficients into a slope. And then set it equal to your.
Yeah, I mean, there's a couple ways you could do it. One of the simplest ones is I've got this equation here, right? The slope is the derivative, right? So what's the derivative? Yeah, so I can take a look at the derivative of that, right? And the angle it's coming in on is theta. So you're just matching the derivative at the boundary condition, third equation. If you're doing a quadratic, I would assume also that if you take the radius here, the light is actually coming out on there. It's actually a fairly good approximation for the spread, you know. And once that does, you'll get a wave when it comes out, right? And you're just measuring along one of those. But that's why that kind of works okay for a quadratic. Now you solve for that one. Now you have an equation. Of course, that's nonlinear. When you get into, you now have the A, B, C's, right? But now you can still stick this into a mesh grid, and you'll get the spreads.
Dr. Schubert, I have a question, sorry.
Sure.
I know you mentioned it, but I missed it. When we're setting the X and Y coordinate system for our parabola, where do we pick that again?
The X and Y for our graph.
So our actual object is going to have X, Y mesh grid, but I assume that's not the X and Y coordinates we're using for the parabola.
No, we're using, this is the actual mesh grid,
Right.
Theta is going to tell you how far the laser has rotated, right? You know this circle, and you know this circle because you've trimmed your thing, right? So you're not taking stuff that's not there. We're just ignoring anything outside your object. You just trim it literally to a beam of that. So you know the outer edge areas of it, which means you know the circle, which means you know the diameter of it, right? You know the center pixel, things of that sort. It gives you a lot of nice stuff. You're making the basic assumption that the laser was aimed right at the center. Did we calibrate that? No, it's probably pretty darn close. I tried, right? So it's a reasonable approximation, delta, whatever it got bumped from my office down to here. Probably not too bad because I was trying not to bump it. So you basically know where this one is. you're gonna set up a grid, right? Since you now know what that object's diameter is, you can rotate, you're gonna take the center of that grid area and you're gonna make that the center line of this. So you're kind of lining it up. That's how you're correlating these to the original grid. You know the rotation angle, because we took them at measured rotation angles, or you take its position. You know, it started at one spot, ended at the other. And so you just, you know, it went through whatever 180 degrees in, you know, 90 frames, right? So each frame is roughly giving you half a degree. In which case I wouldn't take all of them, I'd probably take 4, you know, every fourth one or whatever. You know, it'll vary by how many measurements you get. But you can, by how far it moved, and assuming the motor was moving evenly, it doesn't, but close enough. Assuming your camera takes video with fairly regular frames, not perfect, but it's a lot better than the motor even. So, you know, at that point, you got a pretty good measure of the angle, and by your pixels location, you got a really good figure of the detector location. And that's how it correlates to the grid. Does that make sense?
Yes.
And you just know the laser is exactly opposite your center pixel on the camera. So, and I tried to make the object round so that you wouldn't have any problems correlating where the edge was. Right? There's no weird diffractions or anything of that sort. Those are all great questions, right? And these are things I had to think of when I was making this thing up, that I went in like, how are they gonna figure this out? And so I asked that question, well, what would be a simple way I could figure it out? Now, there could be other ways too. There might even be a more efficient way, right? Well, once I knew I had a way, I knew I could build a system. And then you build a system and you kick it and you discover, guess what? Wow, it would have been smarter to have done this other thing, right? Don't ever feel bad about that. That's exactly why you built the system, to test that out, right? It's that very process of try and fail and come up with a better thing and build that. You know, that's what makes successful products that heal people. You know, it's people willing to get things wrong. So, you know, anyway, you might run into a problem. If you do, shoot me a note on it. What did you find? That's awesome, right? Okay. Do we all feel comfortable that we can solve this problem now? Yay. Okay. So we're actually pretty much at our time. Let's talk, if I wanted to do the diffusion problem, how could I do that one fairly quickly?
Find diffusion problem.
Remember we said that these are like actual equations. What if I wanted to automate a system to be able to do a diffuse where it marks a whole bunch of them?
Oh, the forward path, just
Like that. So we had a cheesy way. Do you remember I made you take a picture from above?
Yeah.
Right? Why?
if you want to just trace every line.
Yeah, imagine, you don't even have to actually trace it. You can do this in an automated way.
Okay.
So imagine this was the picture you took, right? And there's a big, and there's weaker. You pick some level, right? Above that level, we hashtag it in, right? You could pick it whatever. If you remember, it's brightest right along the center line, and it was dropping off, but it kind of got more bulbous, but it diffused more and more. So you pick some intensity level of the red, and it'll cut here. If you picked it a little bit lower, it would go out to there. Right? So let's just say I take that one. Right? Now, I have your object's outline, and I have the emitter's characteristic. The receiver is exactly the same. Right? I could take this same exact thing, and I could reproduce it. I'm going to just do this one in blue, and just forgive me. Right? Here's your line coming in. I can project it to the edge just like we did before, and I can position this same picture, just rotate it so that it's aligned along this axis towards the center. So I just copy and rotate the image. And it's both images are 0 out here and 1 inside here. And now I do OR.
Exclusive or just one?
OR.
Oh, I see.
And what you get is,
Okay.
there you go, that's your light path. Pretty cool, eh?
Yeah, that saves a lot of trouble. Yeah.
No, but you'd have to pre-do all those.
Well,
But yeah, no, I agree, it saves a lot of trouble. But I want you to think, there's a lot of different ways to solve the thing, right? What's the right one? This is gonna be memory intensive, right? Maybe in a professional system, you don't want to do that. But this is gonna be really dang accurate. Right? Because it's actually how it did diffuse.
is that picture on top? Yeah. The last picture.
Right? It's pretty cool too, isn't it? So, you know, you just have to calculate where could the spots be opposite, and you just calculate in one position. Once you have this, you only have to do this for one set, right? Because then you can do rotations. So you just do center to every other possible position in some sense. You know. But I mean, you can do it however makes you happy. You know. But that's a kind of fast, easy graphical one. So if you notice that one, that's very analytic measurement wise as opposed to computation wise. But it is imitating their forward equations. I solved their forward equations, so don't tell Charlie this, right? This is solving the forward equation using an analog computer. What's my analog computer?
Reality.
Yeah, the reality. That's right. I just solved it, recorded what it had at every point, which I can because it's translucent on the top. Right? There's a lot of fun, weird shortcuts like that in life. Don't cut yourself off. So that's another possibility. Right? Okay. We good? Awesome. Hopefully this will save correctly. That.